The next concept is structure of page table. Okay, so before going to structure of page table, let's see some of the sizes of computer. Okay, so how they will be calculated by using binary systems. Okay, so first one, the size of the computer will be measured in 2 to the powers, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Okay, so 2 to the power of 0 means 1 byte, 2 to the power of 1 means 2 bytes, 2 means 4 bytes, 2 to the power of 3 8, 2 to the power of 4 16, 2 to the power of 5 32, 2 to the power of 6 64, 2 to the power of 7 128, 2 to the power of 8 156, and 2 to the power of 9 5 12. Okay, so 2 to the power of 10 is called 1 kb. 2 to the power of 10 is called 1 kb. That means 1024 bytes is called 1 kb, that is 1 kilobytes. Okay, that is 2 to the power of 20. What is mean by 2 to the power of 20? 2 to the power of 1024 into 1 kb, that is 2 to the power of 10 into 2 to the power of 10. Okay, so bases are equal, power should be added, so it will be 10 plus 10 20. So it is called 1 megabyte. Okay, 1 MB. So 1024 of such 1 MBs, we will call it as 1 GB, that is 2 to the power of 30. Then 2 to the power of 40, we will call it as 1 terabyte. 2 to the power of 50, we will call it as 1 petabyte. 2 to the power of 60, we will call it as 1 exabyte. 2 to the power of 70, we will be calling as 1 zettabyte. Okay, so we have 32-bit system and 64-bit system. So it is enough to know until 2 to the power of 70. Okay, so how do we take it? Let us take 4 kb. If someone asks you the size is 4 kb, how to convert it into 2 to the powers? Okay, so you write 4 into 1 kb. Okay, so it will be 2 to the power of 2 into 1 kb, 2 to the power of 10. So it will be 2 to the power of 12 bytes. Okay, 2 to the power of 12 bytes. So in order to represent 4 kb, we need 12 bits. We need 12 bits. 12 bits can represent 4 kb. Similarly, if someone asks you what is 8 mb, okay, if it is 8 mb in the problem, if they ask you 8 mb, then we can simply write as 2 to the power of 3 into 2 to the power of 20, because mb is 2 to the power of 20. So we need 23 bits, minimum 23 bits to represent 8 MB. So how many bits? 23 bits to represent to 8 MB. Similarly, there is a 32 bit system. Okay, so that 32 bit system means it will be 2 to the power of 32. Okay, 2 to the power of 32. That means 2 to the power of 2 into 2 to the power of 30. So what is 2 to the power of 2? 4 into 2 to the power of 30 means 1 GB. So 4 GB can be represented in 32 bits. Okay, 4 GB. So this will be our 4 GB. So if a process size may be in 4 KB or 8 MB or 16 MB, 256 MB, or a process size may up to 4 GB, or it will be 64 bit system, it can take a process size up to 2 to the power of 64 bytes. Okay, right. So the modern computers are mostly 32-bit systems or 64-bit systems, and the process size may exceed up to 16 GB, 4 GB, 5 GB, 16 GB. Okay, and minimum a process size is taking 400 MB, 500 MB. It is taking 50 MBs to 400 or 500 MB, or maximum it is 16 GB, 17 GB, up to lot of GBs. It is a process size is having. Okay, so this is how we need to convert from size to this one, 4 KB to 2 to the powers, and how many bits we can represent that particular size. Okay, so let's see need for page table. What is page table? A page table stores. Okay, what is a page table? The page table consisting of frame numbers. Okay, it's consisting of information of a page where it is present in the main memory. Okay, so if it is a page table that consisting of several uh, entries. Okay, several entries. Suppose that if a process is having 32-bit size, that means how much 32-bit? It is 4 GB size. The process size is 4 GB size. Where it is that 4 GB size? So process size is also called as logical address space, which is also called as logical address space of a space. Okay, so what is the size of this particular process? 4 GB. Okay, how to represent 4 GB? That is 4 into 1 GB, that is 2 to the power of 2 into 2 to the power of 30. So total number of bits to represent that particular process is 32. So look at here, 32 bits needed. This 32 bits of a process size, okay, process size, and each process will have its own page table. Okay, now this particular page table, the logical address space, will be divided into pages, and we also remember that the size of the page is equals to size of the frame, because process is divided into pages and main memory is divided into frames, where the size of the page is equal to the size of the frame. So here, what is the size of the page? It is 4 KB. Size of the page is 4 KB. Okay, so to represent 4 KB, how many bits? See, total 32 bits is 32-bit process size. Okay, in this 32-bit process size, we need, it will be divided into two parts. First one, page number. Second one, page offset. Okay, that is page size. Okay, now what is this one? 4 KB. That means 4 into 1 KB, it is 2 to the power of 2 into 2 to the power of 10. So you will get 12 bits to represent this particular 32. Out of 32, you need 12 bits to represent your page size. And how many bits are remaining? 32 minus 12, 20 bits to represent your page number, right? And these page numbers are indexed to your page table, so that inside the information about frame number will be available. Okay, information about frame number will be available. So total number of pages will be, number of pages equal to logical address space by page size, 2 to the power of 32 by 12, it is 2 to the power of 20. How? It is 2 to the power of 32. This will be go up, and it will be 2 to the power of minus 12. Bases are equal, so you need to add the powers. So it will be 2 to the power of 20. Okay, so total number of pages are 2 to the power of 20. So 0, 1, 2, so on up to total number of pages are 2 to the power of 20. That means 2 to the power of 20 means 1 million pages are there. 1 million pages are there. Suppose that, that is 2 to, this will be your 2 to the power of 20th one. Okay, suppose that each entry, okay, each entry will have a frame number and corresponding information. That is, the page table also contains frame number and valid invalid bit, whether it's a dirty bit, and lot of other information will be there in the page table. So if that information consisting of 4 bytes, assume that it is consisting of 4 bytes of each entry, 4 bytes of each entry, then what is this, the size of the page table? If each page is of 4 bytes, total number of pages are 2 to the power of 20. 2 to the power of 20. So the size will be, what is 2 to the power of 20? 1. So size will be 2 to the power of 22 bytes. What is mean by 2 to the power of 22 bytes? So 2 to the power of 20 means 1. So 4 into 2 to the power of 20 bytes. So 4 into 2 to the power of 20 means 1 megabyte. So 4 into 1 megabyte, it will be 4 MB. So the size of the page table itself, okay, the size of the page table itself is 4 MB. Now look at here, there is a problem. Where the page tables are stored? The page tables are stored in main memory. Where the page tables are stored? The page tables are stored in main memory. The page tables as well as frame tables are also stored in the main memory. But look at here, the size of the page is 2 to the power of 12, that is 4 KB, which is less than the size of the page table, that is 2 to the power of 22, which is 4 MB. This 4 MB of page table can't be fit in 4 KB. Can't be fit in 4 KB. So what we have to do, we need to split this particular page table, okay, into 4 KB, 4 KB, 4 KB. Okay, so that means the 4M, in order, there is a 32 GB process. The process size is 32 GB. Process size or logical address space size is 32 GB. Then to divide this particular 32 GB, we need to maintain a page table where the each page is stored in frame. Okay, so in order to maintain this particular 32 GB process, we need 4 MB of page table. We need 4 MB of page table, but the problem is this 4 MB is more than the page size. This 4 MB of page table is more than the page size or frame size of a main memory. Page size of a processor, frame size of a process. So what we have to do, we again divide this particular 4 MB of page table, this particular page table into 4 KB, 4 KB, 4 KB. Okay, we need to divide this into 4 KB, 4 KB partitions. 4 KB, 4 KB partitions. Okay, right. So we need to divide this into again 4 KB partition. That means 4 MB we can represent it in 2 to the power of 22. So divided by what is the page size? 2 to the power of 12. So this 2 to the power of 12 again this will be 2 to the power of 22 minus 12. We will get 2 to the power of 10. 2 to the power of 10. That is the page table, okay, is divided into one more page table of size 2 to the power of 10 entries. 2 to the power of 10 entries. That means if we have 32-bit system, if we have 32-bit system, the page size is 12 bits, okay, and total number of pages are 2 to the power of 20, okay, that represents 20 bits. In this particular 20 bits, the outer page table, that is this one, the page table is 20 bits. The actual page table is 20 bits, right? So these 20 bits will be split into 10 and 10. Okay, so this will represent outer page table that points to inner page table, the actual page table that points to actual page table. Okay, that means we are splitting the page table into one more page table. Okay, so each entry in this particular page table will point to 1024 entries of other the actual page table. 1024 entries of the actual page table. Okay, right? So we need this. Okay, we need multi-level paging. We need multi-level paging. Now instead of storing the entire 4 MB page table, we can store this particular outer page table that points to one more page table. Points to one more page table. Again, we need to find the size of outer page table. Okay, how many entries in this particular page? 2 to the power of 10. Again, it will require 4 bytes of data. Yes. So again, we need 2 to the power of 12 bytes. 2 to the power of 12 bytes of data. That means 4 KB. Now this particular entire outer page table, the size of the page table is 4 KB, which is equals to the page size. Which is equals to the page size. So this particular outer page table can be fit into one frame in the main memory. Can be fit into one frame in the main memory. Okay. So how this page tables will be structured and divided, we'll see next.